Hello, everyone. Today we will talk about Planar Graph. My name is Thien, and I will introduce you to some of the definition of the graph to get you started. So first, I will give you the definition of a graph. A graph denotes as G equal V and E. V here is a group of vertices. E is a group of edges. For example, if you have a graph of like three nodes here, each of these will be our vertices, which belong to V. And if you have an edge that connects two of them, that will be our edge E, which belongs to the group E. So for each vertex, we'll define degree, like for each vertex V from the set V of vertices, we will define the degree of V to be the number of edge from E that V belongs to the edge, which means like the edge has an endpoint of V. So we would note that as deg V. So here are some special graph. For example, a simple graph. So in the normal graph, we can have some case that there are loops or like multiple edges. But for a simple graph, these will not be permitted or possible. So like simple graph, we just for each two nodes, there could only be less or equal to one edge that connect them, and there are no loops for every vertex. So one other one is a complete graph. A complete graph of n vertices denoted by Kn is a graph of VE such that V is the number of elements in V is n, and for every node in V, for every two node in V, there's an edge connecting them, which means the set of edges will be the set of elements A and B such that A belongs to V and B belong to V. Also, A and B are not equal. So these are denoted by Kn. Another special graph is bipartite graph. Bipartite graph is a graph that for the group of vertices, we can divide them into two groups, V1 and V2, such that the intersection of V1 and V2 is a empty set. So for a bipartite graph, the special about that is that every edge has one element from V1 and the other from V2. For better visualization, I will draw a picture like this. So here we have a set of V1 vertices and V2 vertices. So the edge can only be across these two sets. So we also have a complete bipartite graph, which is denoted as Kmn, where m is equal to m is the element in the vertices set 1 and is a 1 from set 2. Fun fact, if you have a graph such that the number of vertices is 2n and the requirement there is no triangle, then the best number of edge that you have will be the number of edge in K and N. As you can see, visualize here. Every edge across them will be connected and there will be no triangle. All right, back to our stuff. So I will define path. Path is a sequence of vertices like A1, A2, A3 to AN, such that between every AI and AI plus 1, there's an edge connect them. For visualization, these will be a node, and there will be an edge connecting them to form a path. For a circuit or cycle, is a path that start and end at the same point. If you have a path A1 to AN, if this is a cycle, then AN will be equal to A1. Another one. Next, I will define a connected graph. The connected graph is that for every vertex, for every two different vertices, there is a path that connects them. For example, this is a connected path, a graph, because there is a path that connects all of them. But this one will not be, because there are no path between the node 1 and node 2. So now we'll start moving to our topic today, which is planar graph. Planar graph is a graph that can be drawn in the plane without any edges crossing. For example, A4, which is drawn by this, is actually a planar graph because we can redraw it like this one, where no edges is crossing. And for every planar graph, the way we draw it that fulfill the requirement of no edge crossing is called a planar representation. One last thing we need to know about planar graph is region. As you see, the planar graph divide our plane into multiple different regions. For example, of our K4 will be region 1 outside, region 2, region 3, and region 4. The degree of a region is defined as the number of edges on the boundary of that region. For example, the degree of R2 will be 1, 2, 3, so that would be 3. For R1 will be 1, 2, and 3, so that would be 3. That's an edge case such that this one, so the region outside is called R0 will have the degree of 1, 2, 3, 4, and 5. As you see, there's an edge that double counted, and that's just the edge case. So that's all definition you need to understand about planar graph. Planar graph for application in real life is very beneficial in designing a road networks where each cities denote at vertices, and the graph at the edges will be the road that crossing them. All right, so moving on, we will study about Euler theorems.
Hello everyone, I'm Colindres, and I will cover Euler's formula for planar graphs. The formula states that for any connected planar graph, the relationship V minus E plus F is equal to 2 holds where V is the number of vertices, E is the number of edges, and F is the number of faces and or regions, including the outer infinite face. There are multiple ways to prove this formula, but we're going to use mathematical induction on the number of E edges. So first, we'll prove the base case. Second, we'll assume it's true for some arbitrary n equals k. And then we'll prove that if n equals k is true, then it is also true for n equals k plus 1. Let's start with the base case. And let's consider the simplest connected planar graph, which is a tree, which is a graph with no cycles. And within that tree, E is equal to V minus 1. And since it's acyclic, it only has one face or region, which is the infinite or outer face, which means that F is equal to 1. And given our original Euler's formula, V minus E plus F we can substitute v minus 1 for e, and we can then substitute 1 for f, which will give us the equation v minus 1 plus 1. If you distribute the negative, you're left with v minus v plus 1 plus 1. Simplify that, and you're left with 2. Thus, the base case holds. Now for the inductive hypothesis. Suppose v minus e plus f equals 2 holds for some connected planar graph with v vertices, e edges, and f faces. Now we can go to the third step, which is the inductive step. We must prove that if we add one more edge to the graph, Euler's formula still holds. And there are two different ways to do this, which means there are two different cases. Let's start with case 1. If the new edge connects two existing vertices and forms a new cycle, it creates a new face. In this case, E would become E plus 1, F would become F plus 1, and there would be no change in V. V will stay the same. Now, if we recall the formula, we can plug in F plus 1 for F and E plus 1 for E, which will give us V minus E plus 1 plus F plus 1. And if you distribute the negative and distribute the positive, you'll get minus E minus 1 plus F plus 1. And if you simplify that, you're left with V minus E plus F. And by our inductive hypothesis, we know that V minus E plus F is equal to 2. Thus, Euler's formula still holds in this case. Now we move on to case 2. Suppose that instead, the new edge connects to a new vertex. In this case, because there's a new edge and there's a new vertex, V is going to turn into V plus 1, and E is going to be E plus 1. And there will be no change in F because no new face was added, so F will stay the same. And if you substitute V plus 1 for V and substitute E plus 1 for E, you'll be left with the equation V plus E minus E plus 1 plus F. And if you distribute the negative for this equation, you'll be left with V plus 1 minus E minus 1 plus F. Simplify that, you're left with V minus E plus F. And again, by our inductive hypothesis, we know that V minus E plus F is equal to 2. Thus, Euler's formula still holds in this case too. Mathematical induction, we have proven that for all connected planar graphs, V minus E plus F is equal to 2. We can see this in the example of an unfolded cube. So it'll look like this. And we can count the number of vertices. It has 1, 2, 3 right here, 4, 5, 6, 7, 8, 10, 11, 12. So it has 12 vertices. And we're going to subtract the number of edges. And it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. And then we're going to add the number of faces, which is 1, 2, 3, 4, 5, and then the sixth face. And when you subtract and add those together, you're left with 2. And we know this because of Euler's formula.
Good morning, guys. This is Kevin, and I will be presenting to you the section on the 3 corollaries that come as a result of Euler's formula. And these 3 corollaries, they're basically just 3 true inequalities that planar graphs must satisfy. So now here we're going to start with the first corollary, which states that given a connected planar simple graph with E number of edges and V number of vertices, where V is greater than or equal to 3, we get the inequality E is less than or equal to 3V minus 6. So here what I'm going to do is use some basic knowledge and definitions that we know about planar graphs and of course Euler's formula, and I'm going to arrive at what the corollary states. So before we actually begin, we need to know that regarding connected planar simple graphs, the minimum amount or the minimum degree that a region can be is 3. Okay, and we know that because since the corollary holds for connected planar in simple graphs, there has to be at least 3 points that forms a region. So that is one of the key ideas that we're going to use when proving this. And the next idea that we are going to use to prove it is the summation formula for all the degrees of all the regions, which is denoted as regions R degree of R, which that is equal to 2E. And we know this because obviously this is for connected planar and simple graphs. So say we have a graph such as this following graph with 4 vertices, which satisfies all 3 of the traits above. We see that each edge has 2 sides to it. It can be a left side or like a right side, or say for this upper edge, a top and a bottom side. So using that is how you derive at the sum of the degrees of all the regions is 2E. Now is where we begin solving and actually doing the proof for the first corollary. So now we're going to go back to the minimum degree for a region, which we know is 3. Using that, when we're given R regions, we know that 3R is the minimum value for the sum of the degrees of all regions. Okay, and using that, since we know that from the previous summation formula here, since we know that the sum of the degrees of all the regions is equal to 2E, and 3R is the minimum value for the sum of the degree of all the regions, we arrive at the fact that 2E is greater than or equal to 3R. Now, using this, what we're going to do is just simply solve for R, which that yields you with 2 over 3E is greater than R. Now, by rearranging, we solved and got 2/3 E is greater than or equal to R. And here is where we bring in Euler's formula, or the theorem, which is V minus E plus R equals 2. Now, what we're going to do is simply rearrange and isolate R, which we can do by subtracting V and adding E to both sides. So we get R equal to E minus V plus 2. Here, using what we derived, we know that 2/3 E is greater than or equal to R. So what we can simply do is say 2/3 E is greater than or equal to E minus V plus 2. And we know this because R is equal to E minus V plus 2. And since 2/3 E is greater than or equal to R, we can just simply plug that in. And now what we can do is just subtract E from both sides and just combine like terms. That gives you negative 1/3 E is greater than or equal to negative V plus 2. Now we just want to isolate E, which we can do by multiplying both sides by negative 3. And then here we get E, and the inequality flips. E is less than or equal to, we distribute the negative 3, so it becomes 3V minus 6, which this is Euler's first corollary, which we wrote up here. Now I'm going to give you guys an example that shows that this holds. And I'm going to use the complete planar graph, which is denoted with K4. I'm just going to draw it here, the 4 vertices. Just going to simply connect them. And this is a very standard drawing that you'll see oftentimes. And then now what we're going to do is just simply count and plug in. So we see that there's 1, 2, 3, 4, 5, 6 edges. So that's 6. less than or equal to, and the number of vertices, there's 1, 2, 3, 4. So that's 3 times 4 minus 6. And now we just get 6 less than or equal to 12 minus 6, 6 less than or equal to 6, which holds. So there's the first corollary. Now we're going to move on to the second corollary, which second corollary states if G, big G, sorry about that. If G is a connected planar simple graph, then G has a vertex with a degree that is less than or equal to 5. So in order to prove this, what we're going to do is do a proof by contradiction. So for the proof by contradiction, what we're just going to do is just start by assuming that every vertex has degree of at least 6. And then using that to find the minimum value for the degree of all the vertexes summed together, that would just be 6 times v, the number of vertexes. So that is the minimum sum value of degree of all vertices. And then using that, what we're going to do is bring in another summation formula, which states that for all vertexes v that exist in V, the degree of the vertex v, that is equal to 2e. And that you should be able to pretty much tell by intuition, but we know that because a vertex is, let's see, the degree of a vertex is dependent upon the number of edges that it has. So if an edge, say there's an edge that connects to like two vertices, that would add 2 to the total degree because it adds 1 to that to that vertex there and to that vertex there. So that's how you get the 2e. And you can see that that's pretty much, that is identical to the summation formula for the degree of the regions. And now using the idea that the total summation of the degree of the vertices is equal to 2e and that 6v is the minimum sum value of the degree of the vertices, we get 2e is greater than or equal to 6v. However, the corollary states e is less than or equal to 3v minus 6. So using the corollary, you basically want to change it to the same format as what you got. So what you would do is just basically multiply both sides by 2, and that just gives you 2e less than or equal to 6v minus 12. And also earlier, for the proof by contradiction, I also forgot to say that you actually need to assume that the corollary holds. So you would basically be assuming e is less than or equal to 3v minus 6, which is what I used here. So now since I derived that, we can see that this is a contradiction, that 2e less than or equal to 6v minus 12. That contradicts what we got here earlier using the 6v minimum, which states 2e is less than or equal to 6v. And this should be pretty obvious because here it says that 2e is greater than or equal to 6v. But here you subtracted 12 from 6v and 2e somehow became smaller than it, which that is obviously a contradiction. So now it has been proven. And then lastly, what we have is the third corollary, which the third corollary states that a connected planar simple graph with edges E and vertices V, where V is greater than or equal to 3, and there are no circuits of length 3, which what that basically means is there's no cycles of length 3. So that means something like this would not be possible because this is a cycle and it has length 3 because there's 3 of these edges. So going back to the corollary, continuing off, this means, right, it means that each region, since each cycle creates a region, each region has to have at minimum 4 edges. And from that, you get the actual corollary, which is E is less than or equal to 2V minus 4. So what we're going to do to prove this now is since each region needs to have at minimum 4 edges, it means the degree of each region is greater than or equal to 4. So using that to find the sum of the degree of all the regions, you simply multiply that by the number of regions R. So this is the minimum total degree of regions. And then using that, we're going to once again bring back the summation theorem, which states that all regions R, degree of R equals 2E. Now we're going to bring that back. And then we're going to say 2E is greater than or equal to 4R, which we know because 4R is the minimum total degree of all the regions summed together. And the summation formula says that the degree of all the regions added together is 2E. Now, using that, what we're going to do is just isolate E. So E is greater than or equal to 2R because you just divide it by 2. And this is actually supposed to be small r. And then from here, what you can do is just isolate R, and then it becomes 1/2 E is greater than or equal to R. And then here we bring back Euler's theorem, which states V minus E plus R equals 2. And we rearrange that to yield R equals E minus V plus 2. And then here, using what we got when we rearranged earlier, since we know that 1/2 E is greater than or equal to R, simply just plug that in for R, so 1/2 E, and then the equal sign will turn into greater than or equal to, and then that just becomes greater than or equal to E minus V plus 2. Now, once again, as we did with the first corollary, which the proof for this is almost identical, we just want to combine the E's, so subtract E from both sides, that yields negative 1/2 E greater than or equal to negative V plus 2 times both sides by negative 2. Then from there you get E is less than or equal to, because you flip the inequality, and you get 2V minus 4, which that was the corollary as we stated earlier here. So that is the proof for the third corollary, and that means the proof for all 3 corollaries are now complete. But I will give you guys a quick example for the third corollary to show that it holds, basically. And what I'm going to do is I'm going to once again bring back the complete planar graph 4. So let's draw this real quick. Boom. And this is actually an example that would not hold according to this, because the third corollary states here that there are no circuits of length 3. So if there are no circuits of length 3, then that's when this holds. However, here we see that there are indeed circuits of length 3, which, if I can change colors, you can see there's one here. If you travel from this vertex to the top one, and then right, there's, because that's 1, 2, 3. And then you can also do the same, say, from this vertex here to this one over here, across the diagonal and back down, 1, 2, 3. I'm going to plug in to the third corollary, which the number of edges, there are 1, 2, 3, 4, 5, 6 edges. 6 less than or equal to 2 times V. There's 4 vertices, so 2 times 4 minus 4. And we know that 6 is not less than or equal to 4. So therefore, it does not hold for K4, which we know because the complete planar graph of 4 does have cycles of 3. And then now we're going to do an example of a random drawn up graph that it actually does show for. Say I'm just going to draw some points to make sure it satisfies all 3 conditions from the third corollary. Just going to connect these. And okay, now this is connected because all the vertexes are like they're just connected. And then it is also simple because there's no loops and there's only one edge from vertex to vertex. And it's also planar because none of the edges are overlapping. Now we're going to once again plug in the formula. And then what we get is the edges. There's 1, 2, 3, 4, 5, 6, 7 edges. So that's 7 less than or equal to 2 times the number of vertices. There's 1, 2, 3, 4, 5, 6 vertices. And then subtract 4. Get 7 is less than or equal to 8, which 7 is indeed less than or equal to 8. And this holds because, as we can see, there are no cycles with length 4. And there's your example. And all three corollaries are now complete.
Hello, my name is Darwin, and I'll be going through the Kuratowski theorem. So, let's start with the complete graph on 5 vertices, which can be drawn like this. So, as we can see, this graph is drawn with numerous intersection points, and we can redraw this graph a bunch of different ways, but no matter what, we always will get points of intersection. So, this means that the complete graph of 5 vertices is always non-planar. Okay, let's look at the complete bipartite graph with 2 groups of 3 vertices, which can be drawn like so. As we can see, this graph has a lot of intersection points, and it also cannot be drawn without intersection points. So a subdivision, which is a definition you're going to need for this theorem, is when we take an edge and stretch it out by adding new vertices along the edge. We can stretch out this triangle by taking it and adding extra vertices. As you can see, the graph still keeps the same shape. It just has extra vertices. When we do this, we can call these 2 graphs homeomorphic. Again, all that means is basically the 2 graphs have the exact same structure, even if the edges are stretched out into paths. So, if we stretch out the complete graph of 5 vertices, we can see that it still keeps the same shape. It's just some edges are stretched out into paths. And since it keeps the same shape, we can deduce that this graph is also non-planar. The basic premise of the Kuratowski theorem is that any non-planar graph is non-planar if and only if it contains a subgraph that is a subdivision of the complete graph on 5 vertices or the complete bipartite graph with 2 groups of 3 vertices. Now, I'll go through some examples. So, if we take a star graph, we have a center vertice. We connect each one. This graph is very simple, just has one center vertices connected outwards, and there's no way of finding a K5 or a K3 inside of it. And according to the Kuratowski theorem, because there's no subdivision of the complete graph of 5 vertices and the complete bipartite graph of 2 groups of 3 vertices, this graph is planar. Now, this theorem is very powerful because it allows us to look at incredibly complicated graphs and deduce pretty quickly if they are planar or non-planar just by looking for subgraphs of these 2. So, let's look at the complete graph of 4 vertices. Now, even though this graph is fully connected, it's only 4 vertices, which is not enough to make a complete 5 graph or a complete bipartite graph of 2 groups of 3. According to Kuratowski's theorem, the absence of subdivisions of the two restricted graphs means that this graph is planar. Let's look at one more complicated, like the cube graph. Okay, so at first glance, this cube looks complicated when it's because it's 3D. But when we flatten out the cube, we can see it doesn't hide any of the complete 5 graphs or the complete bipartite graph of 3, 3. And again, according to Kuratowski's theorem, since there's no forbidden structure, the cube graph is planar. Let's look at another complicated example. A hexagon with all diagonals. At first glance, this graph does not look like it contains any of the forbidden structures. However, by altering points and removing edges, we can see a hidden complete bipartite graph of 2 groups of 3. So, according to Kuratowski's theorem, since we did find a subdivision of one of the forbidden structures, this graph is non-planar, no matter what we do. To sum up, the Kuratowski theorem states that if a graph is non-planar, it is because you can find a direct or hidden subdivision of the complete graph of 5 vertices or the complete bipartite graph of 3 vertices split into 2 groups.